This comes out of section 8.4, derivatives of log functions. So in this case, we're asked to differentiate f of x equals natural log of sine x. I'll use that chain rule that we talked about in the last example to say, well, it's going to be 1 over sine x times the derivative of sine x, and I'll end up with cos x over sine x. That could be written nicely as one trig function, which is cotangent x, so kind of an unexpected derivative maybe if you looked at that original function. Now the next one I want to take a look at is, what if we have the natural y equals the natural log of x all to the power 5 versus a similar looking example, natural log of x to the 5. Now in the first one, the whole thing is to the power 5, which means when I take the derivative of it, I start by saying 5 times that to the 4. Then I say times the derivative of the inside, which is 1 over x. You could write that a little bit tighter, but pretty much nothing cancels the factors. The second one here, you end up with only the x being to the power 5. So you have the choice here of saying, okay, let's just jump right in, and I'll have 1 over x to the 5 times the derivative of that, which is 5x to the 4. Now if you simplify that a little bit, you end up with just 5 over x. We could have gotten there slightly simpler just by saying in the first place y equals 5 ln x, just by using your log rules to say that power can come out front as a coefficient, which means then that y prime equals 5 times 1 over x, which is 5 over x. So you do get the same answer either way, as long as you haven't broken a rule or invented one of your own. Now the next one, we've got the function, the natural log of x squared over the square root of x minus 3. Now, this is where we really take advantage of the fact that we have a bunch of log rules that work for natural logs or any log base, anything, because if you just jump right in here and say, well, the derivative is going to be 1 over what's in there times the derivative of what's in there, those brackets, you're going to have a pretty complicated derivative. You're going to say, okay, well, 1 over x squared over square root of x minus 3 times, and then use the quotient rule, the chain rule, etc. If you instead start to simplify this thing by saying, okay, well, if you have a division, it's the same thing as having subtraction of two separate logs. If you have powers inside a log, you can say this is 2 ln x, and this one you could even say this is half ln x minus 3. What you find is that your function breaks down into much simpler parts to differentiate, at least to say, okay, well, this first one is 2 times 1 over x, so 2 over x, minus half times 1 over x minus 3 times the derivative of x minus 3, which is just 1. And so you have quite a simple derivative to take that is exactly equivalent to what you would have gotten if you would have done all that chain rule and quotient rule stuff that I was describing, but it's much, much, much easier and nicer to deal with. The last one I want to take a look at here is y equals the natural log of absolute value of x. Now if you recall, you can't log negative numbers, or 0 for that matter. So really what we have here is two cases. We either have the situation where if x is positive, you don't do anything to it, and if x is negative, we have to change it by switching the sign. So if I take the derivative of y equals ln x, we already know that the derivative of y equals ln x, the derivative is 1 over x, and we've done that before. If I try the derivative of y equals ln of negative x and see what happens, I'll see, well, y prime is going to be 1 over negative x times the derivative of negative x, and you turn out to get the exact same thing. And so, which is convenient because it means that if you have y equals ln of the absolute value of x, that the derivative is just 1 over x. So that absolute value really doesn't come into play when you're taking the derivative.